All right. So today we're going to do titrations. We're not going to physically do them. That'll hopefully happen on Monday. But we're going to talk about doing a titration with a weak acid. And you're going to see right away that it is considerably more complicated. And sorry, I'm desk bound today because I forgot to charge my computer last night. So I'm stuck here until it is charged up. But this is, you should have gotten this note yesterday, a handout, and we didn't actually end up doing it. So grab that. If not, it should be in the handout folder. So here's the thing. The titrations we did last year, right? The titrations we did last year, we would typically put our analyte, the thing we were testing, right, in a beaker here, right? So this would be our analyte, which was typically an acid of some concentration, right? We'll say an acid, concentration unknown maybe, something like that, but we have an acid there. And then up here we have, up here we have the base that we were using to do our analysis, right? Okay. And we would drip it in, and as we did so, we would wait for the equivalence point, right? Remember all that? And with a strong acid and a strong base, the equivalence point would be the point of neutrality, and at that point, it'd be pH 7, right? And with one more little drop of base, the pH would go over 7, and phenolphthalein would turn pink, and you'd go, okay, titration is done, right? That was for strong acids and strong bases. But what if the acid isn't strong? All right? So a weak acid titration is more complex. And it's more complex because it's in an equilibrium. All right? So the fact that this is in an equilibrium means that we're going to get strange behaviors, right? Not strange behaviors necessarily, but mathematically complex behaviors, all right? We're going to have to model what happens as we add a drop. So let's imagine before the titration begins, this is just like what we've been doing in the last couple of days. We have got 0.300 molar CH3COOH. Does anyone know what acid that is? Anyone?
Isn't that like lactic acid?
It is ethanoic acid, right? It's got 2 carbons, right? So that would be, you don't need to know this, but here we are. CH3, C, and then that OOH, what does that look like?
It's like diagonal.
Double bond to O, bond to OH. That is a classic carboxylic acid. That is the acidic hydrogen. What's the hybridization state of this carbon? Make sure you review that stuff. It's sp3. Good. What about this one? sp2. Good. Review that stuff if you don't know it. It's not going away. But there we are. That's our ethanoic acid. So now, just like we've been doing, when we have ethanoic acid, CH3COOH, what's it going to react with? An acid needs a base, and the base in this case is always water. Very good. So what do we get on the other side? What do acids do? They give up hydrogen. So what will the CH3COH be on the other side?
CH3COO.
Very good. Charge?
Negative.
Very good. And the bases do what? They gain hydrogen, so it will be H3O plus. Okay, very good. And we can then say that the Ka of our ethanoic acid, right, will be what? Yeah, of CH3COO minus, right? Very good. Multiplied by. Very good. Yep. And divided by. Yeah. Very good. All right. So there we go. And we could look up the Ka of ethanoic acid. I don't think I put it on this note, but in our previous note, we have the Kas way back in this one, right? Our Ka one. So we could look up ethanoic acid. And what do we get for ethanoic acid? Also known as acetic acid. Ka is 1.8 times 10 to the negative 5. So we'll go back here. I would never expect you to memorize that. All right? Never expect you to memorize that. I don't think. I certainly never had to. I guess if you had a prof who was a real curmudgeon, who was really mean. And we know how to do this. We can make an ICE table. And our initial concentration of the acid, is everyone comfortable if I just do HA, A minus, and H3O plus? Is that fine? Just for simplicity. What was our initial concentration? 0.300 molar. And the initial concentrations of these two? 0 and 0. Because we're just getting started, right? We haven't done any chemistry yet. Great. Awesome. Which one of these is going to go up? Which one's going to go down? Great. And are there any coefficients involved? So what will these be? Just X, X, and X. So at equilibrium, this one should be 0.300 minus X, whereas this one should just be, and this one should just be X. And then we could just go and get going. Is there something we could test to make our lives easy? What do we test again? Does the concentration of our acid divided by the Ka, is it, I shouldn't say does, I should say is, that greater than or equal to 500? The concentration is 0.300, and we said the Ka was what again? 1.8 times 10 to the negative 5. That should be going to be a little less than 2, like 1.7 or so, times 10 to the 4. Somebody do that on the calculator. Because everyone's getting a calculator today, which I feel like I've said consistently every day. Right? Again, need a calculator. I want everyone doing the math, not just some people. So if you have a calculator right now, go get a calculator. I want you doing the math, all right? Watching other people do math is not going to teach you to do jack squat, all right? You won't learn a thing. All right, what do we get? Okay, so 1.7, and what exponent? Times 10 to what exponent?
I don't know. I couldn't put
Okay. Well, you gotta. What are you talking about? We're doing chemistry here, and you put the scientific notation in your calculator. If you can't on that one, get one you can. Come on now. 0.3 divided by 1.8 times 10 to the negative 5 gives us, times 10 to the 4. Okay, good. Hey. Boy, still got it. All right, even a broken clock a couple of times a day. Is that greater than or equal to 500? Yes, 17,000 is bigger than 500. Therefore, what can we say? 0.300 minus x we can treat as just 0.300. Good. Does that make sense? Okay. So that's going to make our math easy, because now when we go to do this math, what can I do? This should just be this. Nope, this one here. X. Very good. And the concentration of H3O plus. Great. And the concentration of the original acid. Excellent. No pun intended. And we should get x squared on top is equal to, we just did, we didn't just do that. I can do this, 3 times 1 is 3, 3 times 8 is 24, so this should be 5.4 times 10 to the negative 6. How'd I do? Calculators, everyone do it. Everyone do every calculation. Right, what am I doing here? I'm multiplying this side by 0.30, right? And I'm multiplying this side by 0.300. And so we should get x times x is x squared. And that is that 1.54 times 10 to the negative 6? All right. What do we do now? What do we do? Square both sides? Square root both sides? Yep. Excellent. Very good. That's going to be 2 point something. So x is going to be 2 point something times 10 to the negative 3. 2.3. Awesome. All right. Yeah.
Is there a way to make the calculator like default with you scientific notation? Because mine's not. It's just giving me the full numbers.
I mean, the decimal is fine. Like, if you want to, like, there's nothing wrong with saying here x equals, what do you have, 0.0023? Yeah, that's fine. Nothing wrong with that.
Okay.
I'm sure you can change it. I'm actually not sure how. Okay, so before we titrate, that would be our concentrations. What would the pH of the solution be then? How do you calculate pH? Well, we could fill this in. We know that 3.00 minus 0.0023 would actually be 0.298, right? Does that make sense? So that does change a little bit, not enough that it's going to change our math. And this is 0.0023, and this is 0.0023. Okay. So before we've begun titrating, some of our acid will have dissociated into base, and we'll have some H3O plus as well. How would we calculate the pH? pH is always equal to what? Of what? Yep. What specifically are we looking at? H3O plus, right? And you're exactly right. That means the pH is the negative log of 0.0023. We want to make sure we're doing that. This is going to be 2 point something, 2.8 maybe. Two point six. 2.6 what? We actually have 3 sig figs here.
3.8. So.
Well, actually, I guess we only have 2 sig figs here, which is fine. So 2.6? 2.68?
2.638.
Okay, so 2.6. All right. Cool. So there we go. So before titrating, a 0.300 molar solution of acetic acid has a pH of 2.6. Okay. How's that feel? Not too bad? Okay. Now here's where it gets weird. All right? So that's pretty easy to work with. We start with that. Now the problem is, when we titrate, we're actually really going to mess this equilibrium up. When we titrate, we're going to mess this equilibrium up. How? Well, let's look at it. So, when we add NaOH, we are adding OH minus ions, right? Is everyone comfortable with that? Okay. Those will neutralize some of our acid, but note what this isn't. This is not an equilibrium. This is a reaction that goes to completion. Does that make sense? Acid-based neutralizations are very strong reactions. They don't go back and forth. They're functionally so. Some acid is used up, and then equilibrium happens again. So, this is the tricky part. Look at me. I've actually given you these formulas, which I shouldn't actually even need to do. You should be able to kind of work this out yourself. But the first time through this lesson, I always give the formulas to make life a little easier. All right? If you actually work your way through it, it makes a lot of sense. All right? It doesn't need to be super crazy. But look here. Look here. What we're doing here is we're finding the new initial conditions for a new equilibrium. Does that make sense? All right, look at me again. We added a bunch of base, which is not an equilibrium. It's going to turn a bunch of your acid into its conjugate base, not via equilibrium, but by a strong reaction. That's going to break our old equilibrium. So the equilibrium we just had where the pH was 2.6, that's gone. All right? By adding this base, that equilibrium is no more. We're starting fresh. So what we're going to do here is before we can do an equilibrium, we have to find the new starting conditions. New starting conditions. So the concentration of the acid, which is the concentration of this stuff, is going to go down. This is going to be lower than the 0.300 we started with. Does that make sense? We're going to use a bunch of it up because it's going to react with our sodium hydroxide. How much is left? Well, it's actually pretty complicated because we're doing two things at once. We're reacting some of it away. That's what we're dealing with here, right? Look here. What we're doing is we're taking the volume of the acid that we started with, multiplying by its concentration. That's going to tell us how many moles of acid we started with. We're subtracting from that the volume of the base times the concentration of the base we're adding. We're subtracting away how many moles of it got used up by OH minus. Does that make sense? But then we also have to divide it by a new number because actually what has happened here, we've also just added a bunch of liquid. So in addition to reacting some of it away, we're also adding volume, which means we are, diluting it. Exactly right. So two things are happening at once, which is going to make this math really tricky. Does that make sense? Sneaky math. So it's a twofer. We're reacting a bunch of it away and diluting it at the same time. This equation will actually do both those things for you at once. If I didn't give you this equation, you'd be able to figure it out if you fought with it a bit. But I don't want you to fight with it. This equation will take care of both for you. It will take care of the reaction and it will take care of the dilution. Not a horrible thing to note. This is NaOH neutralizing the HA. and the dilution of adding liquid. You don't have to write this if you don't want to write this, but it'll maybe help you look back and see what's there. If you're going to write it, maybe it would help if I wrote it in letters that were distinguishable as letters and not whatever the heck that was. All right, can we try this? Okay. So, what volume of acid did we start with? Way back at the beginning of this whole process. How much acid did we have? That's the concentration. What was the volume? Very good. Yep, you got them both. So, the volume of acid that we started with was 20 mils. You don't have to convert that to liters because you're going to see that milliliters ends up canceling as a unit anyway. So just don't worry about it. What was the concentration of the acid that we started with? 0.300 molar. Very good. Then we have to subtract the volume of base we've added. This is going to change with every drop. In this particular question, it asks us to do this math after we have added 10 milliliters of base. And in this case, what was the concentration of the base I added? I think it says it in the original question. We're titrating it with a base that actually, to make life easy, has a concentration of... Okay, so we're using the same concentration of base. There's nothing in the rules that says you have to do that. That is just what we happen to have done. Okay. And then down here, you're going to use these two numbers again. What's the volume of acid we started with again? 20 milliliters. But we've diluted it by adding how many milliliters of base? 10. So our new volume is 30 mils. Everyone do this on your calculator. Make sure you can do this in one shot on your calculator. I do not want you to have to do it in steps. All right, you should be able to do this all at once. All right, so plug that in. I want you to get an answer before I do. Again, watching me do math on a calculator, not going to be any use to you. All right, watching someone do math never taught anyone to do math. It's just not how it works. Good, I got the same. So we can say that in our new starting position, the concentration of HA is going to be 0.100 molar. Does that make sense? And that's because, remember, some of our HA has been converted to the conjugate base, not by equilibrium, but by adding the OH minus. Does that make sense? Okay. Which means finding the concentration of that A minus is going to be saying, okay, how much acid did we neutralize? Well, that's just how much base we added times how strong the base we added was. But then we also have to factor in the dilution, the fact that the volume has changed, right? So this math is going to do that same thing. This will calculate A minus from the neutralization and the dilution, right, from adding more fluid. Again, if I didn't give you this equation, I would expect that you'd be able to figure this out. But I give you this equation. All right? I will actually even give you this equation on the test and the exam because I'm a nice guy. But in a university course, they certainly wouldn't. Does that make sense? So be mindful of that fact. But this is the concentration of the CH3COO minus. And it's just going to depend on how much base we added, right? What volume of base did we add? We added 10 mils of base. How strong was that base we added? 0.300 molar. And we have to dilute that to the total concentration of the solution. How much acid did we start with? We started with 20 mils. How much base did we add? 10 milliliters. Cool. At this stage, you can probably predict what this number is going to be.
It's the same.
It is indeed the same. 10 times 0.3 is 0.003. And then we're dividing that by that. And what do we get? 3.0 rather, and divided by 30 is 0.1. Okay. There's nothing magical about these being equal. I happen to pick what we call the half equivalence point, halfway there. Does that make sense? We are titrating 20 mils of a set concentration with something of the same concentration. So 10 mils is going to be halfway there, right? That's why these are halfway to totally having neutralized. There's nothing magical about that spot. I could have chosen after 6 mils and we'd do all the same thing. I wanted the first one we did to have nice round numbers. Does that make sense? That's why these numbers are working out roundly, because I picked a spot with round numbers. In some ways, that's actually a bad spot to pick because these numbers end up being the same. But again, it's nice the first time we do it to not have ugly decimals. Obviously, if you pick anything but this very carefully selected point, you'll have a bunch of ugly decimals. Does that make sense? So it's kind of a bit of a magic trick that I'm having this work out with nice round numbers. It won't always have nice round numbers. This is the note we handed out yesterday, Annie. If you didn't get it, it should be in the handout folder. Oh, you got it? All right, cool. So now these are our new starting conditions. And now you can just do an equilibrium, which you know how to do. So I want you to do that one. These are the new initial conditions. Now find the pH. You know what to do. All right. Now, just like before, we don't have to worry about the NaOH. Those Na plus ions aren't going to do anything. They're not going to matter. And what we're going to have is CH3COOH. You don't even have to rewrite this. It's just the same as the previous page. I'm just going to rewrite it so you have it there to look at. Is going to react with the water in the solution to form even more CH3COO minus and H3O plus, but we have new initial conditions. We're going to look at the initial conditions, the change, and what this will look like at equilibrium. And then we'll look at CH3COOH, CH3COO minus, and H3O plus. All right? And don't forget that what does our Ka equal? Was it 1.8 times 10 to the negative 5?
Yeah. Mm-hmm.
So this is exactly like the last question. The only difference is that we have different initial conditions. I'm going to give you, what do you think, 6 minutes? Is that plenty? Okay, take it away. I'm going to make myself a cup of coffee, not going to lie. This boy needs some coffee. I got to bed so early last night, and I woke up late this morning. I felt so good. I was like, you know what would be really nice right now? To go put the fire on, lie down on my couch, and read a book. So I did. Fire on the couch, and I read my book. I'm rereading To Kill a Mockingbird. Great book. Really enjoying it. If you haven't read To Kill a Mockingbird, you should. And then I discovered something about lying by the fire reading a book.
It makes you sleepy.
Oh, it makes you sleepy. So then you know what I did? I slept for a bit. Then my wife came down and shook me and was like, don't you have to go to work? And I was like, I guess. Guess I gotta go to work. So then I came to work. I'm gonna have a cup of coffee. Yeah, that's the end of my story. It's a good story, right?
Yeah.
Beautiful story.
Until the end.
Is the concentration of the acid, or not the acid, the base also 0.1? 0.3?
Yeah.
No?
What?
The base?
Base.
The one, it's 0.0.
It's on the first page. All this stuff.
0.30? Yeah, 0.30.
I've done something wrong.
Try it again. Don't worry, we'll do it together. So the worst case scenario is you made a mistake. Mistakes are okay. It's part of life. We're all allowed to make them. It's all allowed.
Are you excited for tonight? What the hell is wrong with you? Are you excited for tonight? Milo, are you excited for tonight? Yes, baby. Are you excited? Yes. Also, are you excited? Yes. Milo, are you excited? Are you excited? Hello? Sam's watching. For the first time. So probably. He's sleeping. Or pencil tomorrow. He's just like ignoring himself. In vibes.
I have it. That's true.
I like how you hear the things you're not supposed to. And everything you're supposed to, you never do.
That's not true that I don't do the things I'm supposed to. I struggle with the PA. I will grant you that I struggle with the PA.
Exactly. I would call your name like Mr. Orlando, and your head's like you don't hear anything.
Do I really?
Yeah.
I think like, yeah.
Angela, I think you're a bad example because he'll be doing something and you'll be like, Mr. Orlando, Mr. Orlando. Like, no, even when he's not. Like, he could be walking around the room and have a question.
I'm sorry.
Mr. Orlando,
Oh, do I really do that?
Yes.
I'm sorry. I
No,
don't.
but
I want you to.
so-
I want you to know it's nothing personal.
I'll think about it.
I'll
So
think
terrible
about it.
about it because he will like clearly be doing something or clearly be thinking about something. And you're like, Mr. Orlando, Mr. Orlando. Okay, Mr. Orlando. It is not my fault.
Okay. Let's focus in. Yes.
You said you'd give me announcement privileges so I can make
Oh yes. Remind me. We'll do that together at the end of the period. Okay. But right now. Okay. So, what are our new initial conditions? What's our initial concentration of HA of the acid? Yeah, it's now 0.100, right? What's our new concentration of conjugate base? Yeah, and then again, this is a fresh start. So you don't need to go back and say, oh, it's 0.0023 here. As soon as you started adding in all that base, apple cart upturned. Does that make sense? So you can start with this back. And the truth is, again, we actually should start with this as 1.0 times 10 to the negative 7 in neutral water. But functionally, what can we start with this as? And at all but the craziest of pH values, it's going to give you the exact same answer, 0. All right? Now, we're still going to assume that this is going to go down, that this is going to go up, and that this is going to go up. Because... well, and we could be wrong. We may end up with a negative value of x, which would be interesting. I don't think in this one we're not. But there are times when you guess wrong, and it's like, oh, actually the equilibrium is going the other way. If you ever get a negative x, that's possible. It just means that, oh, this actually isn't going down. It's actually, I misread the equilibrium. It's going to go up. Here, with that Ka value, right, this thing's still going to go down a bit, but not much, right? So anyway, let's take a look. So this should be 0.100 minus x. This should be 0.100 plus x, and this one should just be x. We can save ourselves a lot of time if we do what little test? Yeah. Is 0.1000 over 1.8 times 10 to the negative 5 greater than or equal to 500? If it is, it's going to save us some time here. And of course it is, right? Like we can see right away, this is going to be 5 point something. times 10 to the 4. So it's going to be 5.3 times 10 to the 4. Plenty, right? Plenty big. That is indeed bigger than 500. That is, sorry, 5.5? Okay, that's fine. Point being, real big, right? Ergo, what can we say? 0.100 minus x or plus x, doesn't matter. We can just treat as, yeah. And if I'm being mathematical here, I should really do that, right? Because we're not saying it's not x. No. 0.100, right? Does that make sense? Now, if you didn't do that, you could still do all the math. You're just going to get an ugly quadratic, right? This is going to make our life relatively easy because this one's actually easier than the previous one. Go slowly and carefully for me. What is this value going to be? 0.100. What's this value going to be? X. What's this value going to be? 0.100. Hey, this one happens to work out really.
Wouldn't it be plus and minus x?
Yep, but what did we just check? You're totally right. But what did we just check? Right, we've done this check a bunch. What does this check let us check for? Why do we do it? Go. Oh, okay. By convention, one puts their hand up when they do know, but that's okay. What we're checking for here is x going to end up being small enough that this number is going to be largely unchanged? And this test tells us that, yep, x is going to end up being a small number, so 0.100 minus x is going to still be pretty much 0.100. Right? We've done that a bunch now. Right? We did it in the last question. Right? Okay. So when we do this, this one actually ends up working out really nicely because that will cancel with that, right? And so this one could not be easier. This won't happen very often, but when it happens, take it. What does x equal? 1.8 times 10 to the negative 5. Or, if you prefer, x equals 0.12318, right? Now, first of all, is our assumption correct? Is that going to change 0.100 very much? No, right? That k value is small, right? So at equilibrium then, what does this end up being? This one here, 0.100. What does this end up being? 0.100. But this will be 1.8 times 10 to the negative 5. Now again, I've given you a nice easy one here where lots of things canceled. They will not always be that nice and easy, but we'll be thankful when they are. What do we want to find at this point? The pH. All right. And the pH is equal to the negative log of the concentration of H3O+, which means in this case, it's equal to the negative log of 1.8 times 10 to the negative 5, which means in this case, the pH is equal to 4.7? Oh, yeah, that makes sense. Does it make sense? I like the 4. 4.7. 4.7, right? Negative log of 1.8 times 10 to the negative 5. Negative log base 10 of 1.8 times 10 to the negative 5 gets 4.7. Did I not put enough zeros here? We need one more zero there. Yeah, whoops. Yeah, there should be 4 zeros there, right? Because it's 10 to the negative 5. Well, now those look too crunchy. Like that, right? Okay, how's that feel? Not too bad? So, oh gosh, golly gee gosh. Okay. Well, that didn't go well. Okay. So, a note that if we wanted, oh, I hate you. Just shut up and move. Okay. If we wanted to take note right now, if we're looking at the pH over the volume of base added, so far, what did our pH start at? 2.6, right? At 2.6 was when we'd added no base at all, right? And now by the time we've added 10 mils, our pH is up to what? 4.7? 4.7. Is this relationship going to be linear? Spoiler alert, it is not going to be linear. But we could start kind of graphing that. You know what I mean? Okay. How's that feel? Now, there's going to come a key point, which is if you look up here, we said as we add sodium hydroxide, look at me. As we add sodium hydroxide, what is happening to all of our HA? Not in equilibrium, but just in a good old-fashioned strong reaction, acid-base neutralization. It is getting smaller. It's getting used up. Eventually, of course, what will it reach? This is a strong reaction. If we keep adding OH minus, eventually we will do what with all of this? Use it up. There will come a point where we use up all of the initial acid, not via any equilibrium, but by the OH minus that we're adding. That is the equivalence point. That's what we always called the equivalence point in a normal titration, right? When we'd used up all of the acid with the base that we're adding. Does that make sense? Look at me again. I want to make sure everyone's got this. The equivalence point is when all of the acid that we start with has been reacted away by the base that we've added. Now look at me. Look at me. Don't look at your page. In this reaction, with this setup, how much base do I need to add to reach the equivalence point? We start with 20 mils of acid, and its concentration is 0.300. And we start adding base, and its concentration, I gave you a nice easy one here, is the same, 0.300. When will we reach the equivalence point? When will we have neutralized all of our acid? How much base do I need to add to neutralize all 20 mils of our 0.300 molar acid? 20 mils. Does that make sense? Can we all see that? In this one, it's easy because I made the concentrations the same. They won't always be the same, but in this case, they're the same. The equivalence point of this titration will be 20 mils. All right, does that feel okay? So let's look here. That's going to be our next point. At the equivalence point, this is when enough base is added, in this case, NaOH, is added to neutralize all of the HA. In this case, that is CH3COOH. So we're going to take the concentration of CH3COOH right down to 0. Does that make sense? Now, if we couldn't do in our head that that was going to happen at 20 mils, I've given a formula for that. Look at me. I gave you a formula to find how many mils of base needed for equivalence. Now again, we already did this, but that's okay. What is, in this titration, the volume of the acid that we started with? We started with 20 milliliters of acid. What was the concentration of our acid? Yeah, the initial concentration was 0.300 molar. What's the concentration of our base? And you can see that this particular one is nice and easy. The volume of our base at the equivalence point will be, in this case, those cancel. This couldn't be easier, 20 mils. But it won't always be the same. The reason the volumes are the same is because I made the question. That's very true. And I specifically designed the question so that the concentrations were the same. And if the concentrations are the same, then the equivalence point is going to happen when the volumes are the same. But if the acid is stronger, then you're going to need a higher volume of base. If the base is stronger, then you'll need a lower volume of base. But this formula will get you there. If I didn't give you this formula, I would expect that you could kind of weasel your way around and figure it out. Does that make sense? But I will give you this formula, in part because I don't want this question to take you an hour. You know what I mean? I want you to be able to kind of go through it a bit quickly. But does that feel okay? All right. So now that we've done that, we know that the concentration of our acid that we started with, CH3COOH, that is going to be 0. Does that make sense? We are going to have no CH3COOH. But we will have some CH3COO minus because we've made it. And again, it'll be the volume of base times the concentration of the base. It's going to all be, however much acid you started with, it's going to be that much base. But we also have to take into account that we've been adding solutions, so we have diluted it, right? So let's work this in. You could use volume of the base times concentration of the base or volume of the acid times concentration of the acid here. Either one will work. I've chosen the base because whatever. What's the volume of the base that we've added? 20 mils. What's the concentration of the base we've been adding? 0.300 molar. Good. What is the volume of acid we started with? 20 mils. What's the volume of base we added? No, the volume of base. 20 mils. So altogether we've got 40 mils, which means that the answer is going to be, you should be able to do this in your head, but if you can't, use your calculator. Now that I've said that, dear God, don't let me be wrong. Somebody throw this on the calculator, make sure I'm right. What do we get? Sorry? Okay, good. Now, so when we reach this stage, we usually now will actually use this reaction. We're going to use, it doesn't make sense to talk about, look at me, don't write this, okay? Look at me, pencils down, put them down. All right. We're not going to talk about this reaction anymore. This is just a convention, but why don't we talk about this reaction anymore? What is the concentration of this? Sorry? It's now. Now that we've done all this equivalence pointing, what's the concentration of that? 0. We don't have any. So this reaction isn't going to happen. Does that make sense? Now, I know the reverse reaction can still happen, but the convention is now we work with the reverse reaction, where we say that CH3COO minus that we have lots of now, 0.15 molar, well, that's not an acid. That is it's a base. So it's going to react with water. And what's it going to form? Well, it's going to reform some CH3COOH, but it's going to do so by doing what with the water? Taking a hydrogen from it. Does that make sense? And so what will that water be if it's given a hydrogen away? It'll be OH minus. Does that make sense? You can't work the other way because you can't react something away that's concentration is 0, right? That doesn't make any sense. So if we don't have any of this to start with, The reaction we're going to get is the conjugate base now getting to act as a base. Does that make sense? You could actually do it the other way, but you're going to end up with a negative value of x, and your life's going to be unpleasant. Does that make sense? And I don't want you to have an unpleasant. Annie Novak, do I want you to have an unpleasant life? No, of course I don't. You had a question.
Is the conjugate acid gonna have a charge as well?
No, because when you take this and give it a positive hydrogen, the H plus and the negative of this will make it neutral. That was a great question, by the way. They've all been good questions today. You guys are doing great. How's this feel? Now, remember, that means you can't use Ka anymore. You've got to use Kb. Now, I give you a Kb chart, so it's no big deal. You just go look it up. As it happens, there is a relationship. You can always do Kb is always equal to Kw divided by Ka. So if you do 1 times 10 to the negative 7 divided by the Ka, it'll give you the Kb. But you can also just look up the Kb. Does that make sense? We looked this one up, and what's the Kb here? Okay, very good. So what will my Kb statement be then? Kb, which we know is 5.71 times 10 to the negative 10, is equal to what here? Not numbers, just like the concentrations. Yeah, very good. CH3COOH, the conjugate acid, multiplied by the concentration of? Excellent, very good. Divided by? Very good. So now we just need to make what on the other side? An ICE table. So there's I, there's C, there's E. And there's one piece of good news. That Kb is tiny, so we're almost certainly going to pass our little test here. But what's the concentration of CH3COO minus that we're starting off with? Nope. Of the OO minus. 0.150. The thing that's 0 is the concentration of CH3COOH, and the concentration of OH minus. Really, we should start with 1 times 10 to the negative 7, but mathematically it's going to work for us to just start with 0. Okay. And now, what check could we perform? Well, what's the change going to be? This is going to get used up. These are going to get made, right? So this will be 0.150 minus x. This will be x. That'll be x. What check can we perform here? 0.150 divided by, in this case, what? 5.71 times 10 to the negative 10. Is that greater than or equal to 500? And this number is going to be huge, and huge numbers are bigger than 500. Somebody do the math. It's going to be 3 times 10 to the negative 9-ish. It's going to be a little less than 3. More than 2, like 2.7 times 10 to the negative 9. Somebody do that on the calculator. What is it?
It doesn't give me decimal here.
Yeah, so 2.6 times 10 to the negative 9. Or positive 9, rather. 2.6 times 10 to the 9, and 2.6 times 10 to the 9 is indeed greater than 500, which means we can treat 0.150 minus x as just being 0.150. Good. Okay, and that means that we can actually do some relatively easy math here instead of having to do an ugly quadratic, which we appreciate. What will the top of this be? X times x, which is of course x squared, and the bottom will be 0.150. So this next one will be 1.5 of that. We can do that. That'll be 2.5 plus 5.71 plus what's half of that? Plus 0.35. So this will be 6. 10. That'll be a 5 because I 1 8. 8.56 times 10 to the negative 9. Or 11?
Yep.
Yeah? Okay. And what's that equal on the other side? x squared. Good. If you're wondering how we got that, we of course multiplied by this. We multiplied this by 0.150. And we multiplied this by 0.150, right? Those cancel. Okay, how do you solve this? You take the square root. That's going to be like, it's an odd numbered one, so I can't do that in my head. But it's going to be
9.25 times 10 to the negative 6.
cool. Oh, it's an odd one. You just move that over and make it. So it would have been 81. So I could have, see, I should have been able to do that in my head. But that's okay. That's okay, team. It's 9.25 times 10 to the negative 6. Okay. So that tells us that, is that going to change this concentration 1 iota? Absolutely not. So this will be 0.150. This will be 9.25 times 10 to the negative 6. And that will be 9.25 times 10 to the negative 6. And so if we want to find the pH, can we find the pH directly now? No. What can you find directly? Okay, what does pOH equal in this case? The negative log of the concentration of OH minus, which is obviously the negative log of 9.25 times 10 to the negative 6, which gives me what? 5.03. Yep, I like that. So, what's the pH then? Yep.
8.97.
How'd you do that?
14 minus 5.03.
Yeah, which gives us a pH of 8.97, right? Cool. And if we wanted to keep track of what this looks like now, we would say, okay, if I had the pH versus the volume of NaOH added at 0, at 10, and now at 20 mils, and if we go 2, 4, 6, 8, 10, this one clocks in right up here. The previous one was 4.6, right? And before that was 2.6, give or take. So we're getting a graph that looks like that. Clearly not linear, right? A nonlinear relationship. Yeah. What do we know about pHs? The pH and the pOH have to add up to 14. So if you want to find one or the other, you can do 14 minus the other, right? pH plus pOH always add up to 14 in water at 25 degrees Celsius. That number shifts a little bit as you change temperature, but not at reasonable temperatures. That's a reasonable approximation. Yeah.
So if the temperature is, like if it says in the question the temperature is like really high, what do I do?
You would have to shift that, yeah. You can look it up too. You can look the kW of water up at different temperatures. And then you wouldn't be able to do the 14 shortcut. You'd have to actually do, remember that kW always equals the concentration of H3O plus times the concentration of OH minus, and you'd figure it out that way. Do you remember that? We've done that a few times. Cool. Good questions. These are very good questions. Any questions about that? Here's the nice thing. That's the last hard one. After this, it's plain sailing. Look at me. After this, it's plain sailing, because after this, there's no more equilibria. After this, you're adding NaOH, and NaOH isn't a weak base. NaOH is a strong base. And after this, there's nothing for it to react with, right? Because you've used up all the acid. So the good news is, after the equivalence point, you don't have to do any equilibrium chemistry. After the equivalence point, there's no equilibrium to worry about. I mean, the truth is there's still a tiny bit of equilibrium to worry about, but it's so, with the conjugate base left behind, but it's going to be so weak relative to the NaOH that you're adding that you can ignore it completely and it'll be fine. So at this point, we're just doing that. Now, this may look complicated, but really all we're saying is that we only want to worry about the base that we used up after the equivalence point. So look at me. Everyone look at me. All the base that we used up to and including the equivalence point has been gone. It's gone. It's reacted away. Does that make sense? So we have to subtract that away to be like, now if we've added, let's say after 27 mils total of NaOH. So how far past the equivalence point is that? Our equivalence point was how many mils again? 20. So how many mils past that have we added? The equivalence point was 20. We've had a total of 27 mils. So we're how far past the equivalence point? 7 mils. That's all this bit of math is doing. And then all we have to do here is make sure that we dilute it because we started out with water, right? Does that make sense? So if we want to know the concentration of OH minus, it'll be easy. We just say, okay, how much base have we added total at this point? How much base have we added total at this point? All right, 27 mils. What was the equivalence point? In this case, it was 20 mils. What was the concentration of our base? Way back to the beginning of the question, what concentration are we working with? 0.300 molar, right? And then, if we've added 27 mils of base total, how much acid did we start with? How much acid did we start with? No, I don't think so. Go back to the very first page, beginning of the question. 20 mils of acid. That's important because we have to remember, even though that acid isn't an acid anymore, we've neutralized it, the volume is still there, so it's going to serve as a dilution, right? So we can't ignore it, or we would be ignoring that 20 mils of water from that acid. And we can do this. 7 times 3 is 2.1. 2.1 divided by 47 is going to be, I don't friggin' know. That's going to be on the order of 0 points less than 5, 0.4-ish. 0.45. Okay. Do we have one extra decimal?
4, it then be 0.446.
446? Great.
Oh, 7. There's an 8.
Okay, that's fine. Just because we're still going to use this to calculate pH, so it's always nice to keep an extra sig fig, right, until you're done. All right. Therefore, to calculate the pOH, we would just say what? The negative log of the concentration of OH minus, which in this case is the negative log of what? 0.447 molar. And that's obviously going to be 1.3.
Oh, no. How many secrets do I have?
2.
Okay, 1.3.
All right. There we go. Whew. How's that? One question, team. Only took us 60 minutes. That's pretty good, right? Now listen, these won't take you that long, but they do take you time. So now, for homework, and we're going to pick a different acid. So let's go to our acids. Let's pick, I don't know, formic acid. Sorry? What did you want? You want nitrous? Okay, we'll do nitrous. Sorry. Okay. We'll say nitrous. What is the pH of, we'll say, a 25 mils of 0.200 molar nitrous acid? And then we'll say, when titrated with 0.100 molar NaOH. And then we're going to say A before titration. B after, okay, let me just quickly look. We'll say after 20 milliliters. C at the equivalence point. And D 10 mils after the equivalence point. So that's exactly what we did this note. Now, your homework question has ugly numbers, all right? Not super ugly, right? But uglier. Can we all agree? Now listen, I'm going to give you a tool that I made. I made a thing, team. I made a thing. And listen, if Kelford had made the thing, it would probably work better. But I made a thing and I did my best. Ready? Can I show you the thing I made? So I'm going to share it with you, and I'm going to encourage you to use it because it can make your math a little easier. Here it is. All right, ready? Can somebody give me the Ka value of nitrous acid? Nitrous acid. I'll get it. Team, I'll get it. You know what? Allow me. But everyone look here. I want everyone to look and pay attention to this, all right? Because it's going to save you. And then you're all going to complain and be like, oh. Would you like to hear what you're going to be like again? So 7.2 times 10 to the negative 4. There we go. All right, now listen. You can actually put all the information here. In this question, I'm going to do something different, all right? I'm not going to give you the one we just made. Let's say we had 50 mils, and let's say its concentration was 0.500 molar. Does that make sense? Then, let's say that we had a strong base that had a concentration of 0.35 molar. Does that make sense? Now, look what this does for you. This will actually give you a titration. It will show you the equivalence point, and it will show you the pH at each value. It'll show you all that, and then you can even put in the volume you want. Look here, 0 before the equivalence point, and it actually makes the ICE table for you. It does all the math. It does the quadratic, so it doesn't even do a shortcut, and it gets all the values for you. Does that make sense? And then you can say, what about after 2 mils? What about after 55 mils? And then this has an annoying equivalence point, this one I came up with. 42857143, which annoyingly, I picked a bad example for that. I'm going to change this to 0.5 molar as well, because if they're the same concentration, what will the equivalence point be in this case? Team? It'll be 50. And so if you actually nail it, it will even give you the concentration at the equivalence point, and you'll note that it's doing the base equilibrium now. Does that make sense? So this will answer the question for you. Now, do I want you to use it to answer the question? No, that would be stupid, right? Why am I giving you this tool then? To check your answers. Does that make sense? So I encourage you to use this to check your answers. I encourage you to use it not just to give you the answer, but you're going to find it to be a useful tool. Oh my goodness. Will do, Aiden Anderson. So, guys, listen. This is the last skill in this unit, but she's a doozy. Yes, we can agree?
Is this the last one that usually goes to yes?
Yeah. So day 2, we're going to actually do it. Like we're going to go titrate a weak acid.
Oh, are we doing lab books?
You're going to staple something in. Be a nice, easy one.